Exercise 16. If you have an earlier version of this textbook, you might have a typo where it doesn't say sigma finite here. You need sigma finiteness because saying f equals d nu d lambda, that requires Redan-Nikodym, which doesn't even apply unless the measures are sigma finite. So, let's begin. Let f be d nu d lambda. Now, let A equal this set of points x such that f of x is less than 0. We want to show that this has mu measure 0 so that, because we're trying to prove that this holds. So assume for contradiction, which I will abbreviate by AFC, that lambda A is greater than 0. Then nu A is equal to the integral over b of f d lambda. Well, this has to be less than 0, which is impossible. Wait, let me just make sure that this makes sense. Right, assume that this is greater than 0, then this has to be less than 0 because there has to be some region on which, because f is strictly less than 0, there's got to be some region on which it's bounded away from 0, and you integrate over that region and you get that this whole thing has to be strictly less than 0. But this is impossible since nu is a positive measure. I'll write positive here just because it's sometimes not clear in these problems whether our measures are positive or signed or whatever. Thus, lambda A equals 0. And since lambda equals mu plus nu, we know that we know that mu of A is equal to 0 because nu is a positive measure, so it can only add to the measure. Anyway, so that takes care of showing that f is greater than or equal to 0 mu almost everywhere. So let's see here. Next, let B equal the set where f is greater than or equal to 1. We want this to have mu measure 0. Since nu is sigma finite, there exists a sequence Bn of sets such that the measure of the Bn's is equal to B, and nu of Bn is finite for all n. Then for all n, I'm leaving out the quantifiers for all n because it's a little, I think it's kind of obvious. But anyways, nu of Bn is just by definition the integral over Bn of f d lambda. But this is, because f is greater than or equal to 1 here, this is greater than or equal to this. And, well, this is just equal to lambda Bn, which by definition is mu Bn plus nu Bn. So what we can do is we can cancel here because mu Bn is finite, and that tells us that mu Bn is 0. Thus, mu B is equal to 0 because B is a countable union of sets of mu measure 0. Hence, 0 is less than or equal to f is strictly less than 1, mu almost everywhere. Next, note that if lambda E happens to be finite, then we can write mu E equals lambda e minus nu e. When I say we can write this, I mean writing this out, this is actually defined. This is not going to be infinity minus infinity because lambda e is finite. And so, anyways, what is this? This is the integral, well, just by definition, this is the integral of 1 d lambda minus, and then you can write this as the integral of f d lambda. But then we combine these integrals into 1, get 1 minus f d lambda. Alright, so that will give us what we want at the end, but this is only for the case of lambda e finite. See here. So let's see here. I have written in my notes that let lambda e be finite, but we just took care of that case. So now what we need is now for any e in script m. No, I was right. So this holds. So furthermore is not how you write it. What you write is this, since 1 minus f is not equal to 0, mu almost everywhere, we can write integral over e of f 1 minus f d mu. This is fine because we don't have to worry about dividing by 0 because that can only possibly happen on a null set. And even if so, you could just set it to whatever you want and it wouldn't affect the integral. But then, because of this previous calculation, we can replace mu with 1 minus f d lambda. And so, this is true. And then, let's see here, where do we go from here? But what is this? We just cancel. This is the 1 minus f's cancel, and we just get the integral over e of f d lambda. But that's new. So, this is equal to nu of e. Now we extend to arbitrary e in m. So for arbitrary e in script m, let xn be such that xn increases to x, increases in the terms of subsets. So x1 is a subset of x2 is a subset of blah blah blah. And lambda of xn is finite for all n. Now let en equal e intersect xn. Then since lambda en is finite because it's less than lambda xn, we have nu of en is equal to integral over en f over 1 minus f d mu by what we just proved for the finite case. But now the sequence of functions f1 minus f indicator of en increases to f1 minus f indicator of e pointwise. So by monotone convergence we have nu e equals integral over e of f1 minus f d mu. But what does this mean in terms of d nu d mu? This means precisely that d nu d mu is equal to f over 1 minus f. And there we go. This completes the proof.